Hello my dear students, welcome back to your favorite and India's most affordable learning platform, Physics Wala. So in today's session we are going to cover the lecture number 5 in motion in a straight line. So this is going to be the last lecture in motion in a straight line. So we just understand first the Galileo's law of freely falling body, and we'll understand the trick related to this, and then we'll do the summary of whatever we learned till now in the motion in a straight line. Okay, so then I'll provide the practice sheet. So about 30 questions I'll provide. So those 30 questions you should solve. Okay, so with that the total motion in a straight line will be done. So in the next session onwards we'll see the motion in a plane, so where we'll first start with the vectors, and then once we understand the vectors concept, so then we'll go for relative velocity, so then projectile motion, clear, relative velocity in 1D, relative velocity in 2D, so different kinds of concepts related to relative velocity, and then projectile motion. So then we'll wind up the total kinematics part. Okay, chalo. So today's topic, today's goals, so we have two goals. First, let's understand the Galileo's law for freely falling body, and then this summary of the total motion in a straight line. So as usual, for the next 1 hour, it's not going to be 1 hour lecture also, it's going to be shorter one today. So just we are going to see the summary. Okay, so till whatever the time that I am going to teach, so be with me for that time and avoid all the disturbances around you guys. And at the end, so it's very important to write the short notes. So that's very important. Okay, chalo. So let's start with the Galileo's law of odd numbers. So here this law says that whenever the successive distance covered by a body dropped from some height, the successive distance dropped by a body from some height, so will be in the ratio. See here, the distance covered in the first second. Let's suppose a body is dropped. So then the distance covered in the first second, how do you find? So the distance covered in the t seconds minus distance covered in the 0. So distance covered in 1 here. So the distance covered in 1 second minus the distance covered in 0 seconds, which is going to be the distance covered in the first second. So the distance covered in t seconds is nothing but half gt square. Dropped means you can simply consider its initial velocity as 0. Dropped means its initial velocity u is going to be 0. So if u is 0, so then we can simply write s1 is equals to half gt square, so which is equals to, this is however 0. So in some time t, so they are asking half gt square. So let it be. Then, so in some time 2t, like in the first second, the distance covered in some t seconds. Okay, this is the distance covered in t seconds, let it be s1. And the distance covered in total 2t from here to here. So the distance covered in 2t, so which is going to be the distance covered in 2t minus the distance covered in t. This is the distance covered in 2t. So now if you need the distance covered in S2, if you need S2, so what we do is S2t, sorry, this is going to be total 2t, right? So now, so if you need the distance covered in 2, this S2 if you required, so what we do, S of 2t minus S of t. So from this total thing, if you subtract this part, we'll get this only. Just understand the logic. So we are not doing any complex, we are not doing any complex thing here. Just the simple logic is, when a freely falling body or a body is dropped, so then the distance covered by it in t seconds, let it be s1. So in total 2t seconds, let it be s2, and total 3t seconds, let it be s3. So that's what we assumed. Okay, now so the distance covered in the first t seconds, that's s1, which is equals to distance covered in t seconds minus distance covered in 0 seconds. So we got half gt square. So now the distance covered in 2t seconds, so this we required, so which is nothing but the total distance covered in 2t minus the distance covered in t. Okay, so that's what we wrote. So then as it is a freely falling body, so s2 will be equals to, I can say initial velocity is 0, so then half g, in place of t write 2t whole square. Okay, so minus, so the distance covered in t, so the distance covered in t is half gt square. So this is going to be 4 gt square minus half gt square. Yes or no? So this is 4 into half gt square, this is minus half gt square, which is going to be 3 into half gt square. So which is nothing but 3 times the S1, shall I say? 3 times the S1. Similarly, the distance covered in third one, S3 if we required. So what we do? So if you need S3, so simply the distance covered in total 3t, the distance covered in total 3t minus the distance covered in 2t, right? So then this is going, u is however 0, half g, in place of t substitute 3t whole square minus, so this the distance covered in 2t. So what is the distance covered in 2t? Already we got 3 half gt square, 3 into half gt square. So this is going to be 9 into half into gt square. So minus, so this is going to be 3 into half into gt square. Yes or no? Yes. So 9 minus, so this, sorry, this is how much? 3gt square, right? S of 2t. What is the S of 2t? We got, just a minute guys, the distance covered in 3t minus the distance covered till 2t. Yeah, so till 2t, how much it is? Only in the S2 it is half gt square. So but the total S2, S of 2t, it's going to be this plus this, right? Till here it's going to be half. So this is, understand this thing properly, so this is going to be half gt square. This distance is 3 into half gt square. So now this total distance will be 4 into half gt square, 4 into half gt square. So now S3 means you have to write, so S in 3t minus S in 2t. So the total distance covered in 2t will be, so half 4 into half gt square. So this is half g, so in place of t, let's write 3t. So whole square minus this whole thing is 4 into half gt square, right? So now see here. So this is 9 into half gt square minus 4 into half gt square. So which is nothing but 5 into half gt square. Okay. So now simply, so what I am going to tell the conclusion here it is, so whenever a body is dropped, for example, a body is dropped from some height, here the body is dropped. So now let's suppose in some t1 seconds the body has covered some s1 distance, and then some t2 seconds where this time interval should be same. So some t2 seconds, so let's suppose the body has covered some s2, and then so let's suppose some t3 seconds the body has covered the distance s3. So where this t1, t2, t3 must be same, so the time interval must be same. So if a body is dropped, so in successive time intervals, so it covers some distances. So then the relation between these distances are given by, so the S1, the first one is S1 if you consider, so this S2 will be equals to 3S1. S1 is equals to, let it be S1, so the S2 will be equals to 3S1, whereas S3 will be equals to 5S1. And if you take the next one, so it's going to be 7S1. So the next one 9S1. So like that, so the ratio of their distance covered, so will be in the odd numbers ratio, 1:3:5:7 and goes on. That's what we wrote here, the Galileo's law of odd number. So whenever a body is dropped from some height, so and then in regular intervals, if it covers some distances, so then the relation between those distances will be given in the ratio of the odd numbers, 1:3:5:7:9 like that. So it continues. Okay, so this is the concept you should remember. So what is the importance of this, sir? So in the last class we solved some questions, right? So 2 questions I solved based on this concept. So now I followed the procedure actually there, but without following the complete procedure. So you can simply do it through this trick. Okay, so what's this trick? See here, understand this question. A stone falls freely under gravity. It covers distances h1, h2, h3 in the first 5 seconds, next 5 seconds and next 5 seconds. So the relation between h1, h2, h3. So what we did, first we found the h1, right? S is equals to ut plus half at square. So then S is equal, then we found the h1. Then we did h1 plus h2 distance. So then in the third case we did h1 plus h2 plus h3. From there we got what is h1, what is h2, what is h3. So then we established the relation between those h1, h2, h3. So that's a lengthy procedure. But without going for that procedure, you can simply do this question just by looking at it. See here. So the distance covered in the first 5 seconds is h1. See, a body is dropped. A body is dropped. So the distance covered in the first 5 seconds, let it be first 5 seconds. So which is going to be h1. So the distance covered in the next 5 seconds, which is going to be h2. So and the distance covered in the next 5 seconds, so which is going to be h3. So like that we have 3 distances covered in regular intervals of time. This is important. So if the times are changing, you can't apply the Galileo's law of odd numbers. So the time interval should be same. So simply shall I say here the ratio between h1, h2, h3, so which is going to be, so 1:3:5 directly, 1:3:5. So that's why the h1 is equals to h2 by 3, which is equals to h3 by 5. So you can write, so the h1 is equals to 3h2, which is equals to 5h3, right? So that's what we have seen in the last class. So and then the relation is simply, the relation is simply this one, 1:3:5. So without going for the procedure, you can simply do it by this trick, Galileo's law of odd number. So one thing you should note, that is the time interval should be same for Galileo law of odd numbers. So time interval should be same. So the time interval should be same. Okay, clear this part? Sure. Next. So this question also you can do it easily by this Galileo's law of odd numbers. See here. So this question we solved in the last class. So the water tap question, right? So the water drops fall at regular intervals. See here, this is important. At regular intervals from a tap. So let's consider this is a tap. So this tap is 5 meters above the ground. So this tap is 5 meters above the ground. Now, so in the question what they are saying, so the third drop is leaving the tap at an instant when the first drop touches the ground. So when the first drop is about to touch the ground, so the third drop is releasing. So this is the third, this is the first. So in between the second drop will be there. So they said at regular intervals of time, at regular intervals of time. So the time gap between this and this is going to be t. The time gap between this and this is going to be t. So now what I need actually, so how far above the ground is the second drop at that instant? So when the first drop is touching the ground, so how far above the ground the second drop is? So this distance we required. This is how much? That's what they are asking. So here first thing that you should understand is it's a water drop which is freely falling. This point, and then the time interval is same. Here if it is time t, here also it's going to be time t. Yes or no? So now what I am considering is, let's suppose in the first t seconds it covers a distance x, let's consider. So in the next t seconds it's going to cover the 3x, obviously 3 times the first one. Yes or no? Just now we have seen, right? So if the distance covered in the first second is let it be x, so then the distance covered in the second will be 3 times the half gt square, which is going to be 3x, right? And the distance covered in the next second, so this is s3 actually. So s3 is equals to 5 times the x. Yes or no? So that's why here see simply this is x, this is going to be 3x. So we know the total distance which is 5 meters. So x plus 3x is equals to 5 meters. So from here 4x is equals to 5 meters, and then x is equals to 5 by 4. So x is equals to 1.25 meters. So x equals to 1.25 meters. So what is this x? The distance from here to here. So but what we required? So how far above the ground is the second drop? So we require this distance. So what is this distance is going to be? 3 times 1.25, or else you just subtract 5 minus 1.25 you do. So in the both cases you are going to get this 3x is going to be 3.75 meters. So this distance we required. So which is option C. So in the last class we followed the procedure actually. So here simply you can apply the Galileo's law of odd numbers. Yes or no? Understanding? So in the competitive exam we required this kind of tricks. Okay. So because the time saving is very very important, Galileo's law of odd numbers we applied here. Hope everyone clear with this till now. Right? So this is a Galileo's law of odd numbers. So now with this, so we completed the motion in a straight line. So I did maximum number of questions, okay, and every concept is covered. So some concepts are there related to relative velocity, so that we will cover it in the motion in a plane. Okay, once I deal with the vectors. So when I deal with the relative velocity after vectors, I'll deal with the relative velocity. At that time, so we'll understand, so like collision process, and then when these two balls are going to be meet. Let's suppose one ball is thrown up and one ball is dropped from the top. So after how much time, so those two balls are going to be meet again. So that those kind of questions we can solve by relative velocity. That will be easier process. So there we'll discuss about those problems. So now let me go for the summary of the total motion in a straight line. Okay, so this is very very important. Let's go for the summary. So let's start from the basics. So first, where did we start in the motion in a straight line? So come by the sequence. So first we defined what is distance, what is displacement. So the distance is the total path covered by the body, and displacement is the shortest path covered by the body. And we also know that the distance will be always greater than or equals to displacement, or the numerical ratio of distance to the displacement will be greater than or equals to 1. These are the just basics, right? So the distance to displacement ratio will always be greater than or equals to 1. Yes or no? So just write along with me. So this summary is very very important. We are just summarizing the whole chapter now. Okay. So next. So we know that distance is a scalar quantity and displacement is a vector quantity. So that is units are so either in meters or centimeters or kilometers, whatever. And the dimensional formula is L to the power 1, right? M to the power 0, L to the power 1, T to the power 0. So this is about the distance and displacement. So now let's come to the next one. So that is speed and velocity. So the speed is going to be simply, it's a distance by time and it's a scalar quantity. Distance by time. So whose dimensional formula, so shall I write here? So the distance is m to the power 0, L to the power 1, and then T to the power minus 1. L to the power m to the power 0, L to the power 1, so by T to the power minus 1. So that's a speed. And then so same we can write it for the velocity. So velocity is nothing but the displacement by time. It's a displacement by the time taken. So which is nothing but we can write, so that again the dimensional formula is going to be same, m to the power 0, L to the power 1, T to the power minus 1. And we know that this speed is a scalar and velocity is a vector, and units are going to be either meter per second or kilometer per hour. So here also the same thing. Now so next comes the point, that is what is average velocity and what is average speed, right? So average speed is nothing but total distance by total time, right? So the average speed is total distance by total time. So and then the units are going to be same and dimensional formula is going to be same, and then this is, let's write distance. So next, so the average velocity, which is equals to, so total displacement by total time. the total displacement by total time, right? And we also know that the distance can be 0, positive or negative. The displacement can be 0, positive or negative. So but the distance is always positive. So as the displacement can be 0, so the average velocity can also be 0, but average speed can never be 0, okay, because the distance can never be 0, right? So and then, so here the important cases we have seen. So what are the different important cases that we studied? So let's suppose a body has started from point A, so then it reached point B with a velocity v1, okay, and then so again in the return journey, so it covered with a speed of v2. So while going, its velocity is v1, while returning, its velocity is v2. So in this case, what is the average speed? So the first thing is the average speed is going to be 2 v1 v2 by v1 plus v2, yes or no? So whereas average velocity is going to be 0. The average velocity is going to be 0 because the body is returning to the same point. This is clear, everyone? Sure. So in the same result it holds true for if a body covers some distance with velocity v1 and next equal distance it covered with velocity v2. So let's suppose this is A, B, C. So then, so the what is the relation between this v1 v2? So the v average which we write, so is going to be 2 v1 v2 by v1 plus v2, yes or no? So here average speed and average velocity, they both will be same. Here average velocity and average speed, so this is average velocity or average speed, both are same. So why? Because the body is moving in the straight line. So that's why here average velocity will not become 0. In the previous case, here average velocity is 0 because the body is returning to the same point, but average speed is 2 v1 v2 by v1 plus v2. So this is also clear, everyone? So these are the results that we have seen. So now, so later what we discussed about the acceleration. So what is acceleration? The acceleration is equals to, so the change in velocity by time, the change in velocity by time, yes or no? So and what are the units? We know that the units are meter per second square. And what are the dimensional formula? Let's write along with me. So however, so m to the power 0, right? So and then L to the power 1, T to the power minus 2, yes or no? So this is going to be meter per second square. Meter means L to the power 1, second square means T to the power minus 2 if it comes up. So that this is the dimensional formula. And then, so later we discussed about, so what is average, what is instantaneous velocity, yes or no? So what is instantaneous velocity and what is instantaneous acceleration? So now the term that comes, that is instantaneous velocity, so which is equals to simply ds by dt, the slope of st curve, the slope of st curve, it results in the slope of st curve results in the instantaneous velocity. So if the displacement versus time graph is given, so at any instant if you require the velocity, so simply just draw a tangent at that point. So then the tangent, let's suppose that it makes angle theta, so which must be slope is equals to tan theta formula, right? So this also we discussed clearly. And then we also discussed the instantaneous acceleration. So the instantaneous acceleration, so what is instantaneous acceleration? Simply the dv by dt, so the slope of vt curve will result in the acceleration, right? Which acceleration? Instantaneous acceleration. So the units and dimensional formula are going to be same for average acceleration or for instantaneous acceleration or simply acceleration, whatever it is, okay? Sure. So now, so from here I can write, so if you have to get velocity from the displacement and acceleration from the velocity, so then I can write like this. So this is going to be ds by dt, this is going to be dv by dt. The slope of st curve with sorry guys, so the slope of st curve results in the velocity. This is, so slope of, I can write like this, slope of st curve results in the velocity. Here it is slope of vt curve results in the acceleration. Yes, and the reverse process also we have seen. What is the reverse process? If the velocity is given, they asked you to find the displacement, so simply the integration of v dt. And then, so if the acceleration is given and they ask you to find the velocity, so then the integration of a dt, the integration of a dt. So what is the integration meaning? Area under the curve, right? So that's why the area under vt curve, area under vt curve, so it results in what? Displacement, distance or displacement, right? So whereas the area under at curve, area under at curve, so this results in, so the velocity. Clear? Understanding this process is important, and we solve many questions based on this. And then, so we have also seen one more expression for the acceleration. What is that expression? A is equals to v into dv by dx, where when to use this equation? Whenever the velocity is given as a function of displacement, whenever velocity is given as a function of displacement, so then simply use this one. So the acceleration is going to be v into dv by dx. So these parts are clear, everyone? Just the basics, whatever we have seen till now. So these are the basics. So and then, so whatever the equations of motion, what are the equations of motion? V is equals to ds by dt, a is equals to dv by dt, or a is equals to v into dv by dx. So these are always valid. Yes or no? So this v is equals to ds by dt, a is equals to dv by dt, and same a is also equals to dv by dx. So these are the equations of motion which are always valid. Okay, so but so there are some equations so which are valid only in uniform acceleration. So the equations of motion under uniform acceleration. So the equations of motion under uniform acceleration, under uniform acceleration. So which is, we can write v is equals to u plus at, then s is equals to ut plus half at square, then so v square minus u square is equals to 2as. So these are the equations of motion under uniform acceleration. And then based on these, so we discussed about some standard results. So what are the standard results? Tell me, what are the standard results that we discussed? Let's suppose a body has started from point A and then it reached point B, let's suppose. So and then the velocity of this at A is v1, so the velocity at B is v2. So now what is the velocity exactly at the midpoint? So the C is a midpoint. So what is the velocity at this midpoint? So let the velocity be v. So what is that v formula? So the v is equals to square root of v1 square plus v2 square by 2, right? So this is the standard result that we have seen. And then, so one more term, the retardation, I missed it actually. So the retardation, here you can write. So where the retardation is negative of the acceleration simply. The retardation is simply the negative of the acceleration. Yes or no? Understanding, guys? Sure. So and then, so one more important result that we have seen in the last class. So that is, if a body moves with a speed u and then some braking force applied, so let the distance covered by it is s. So then, so if the same body moves with a different speed, let it be nu speed, n times this speed. So then if the same braking force is applied, so after how much distance it will stop? So this is a final velocity 0. Here also the final velocity 0. So let the distance covered by it is s dash. So after how much distance it stops? So which is going to be s dash is equals to n square times the s. So the s dash is equals to n square times the s. Clear? So this result also we have seen. And then so later we also covered the distance covered in the nth second. The distance covered in the nth second. So what's the distance covered in nth second formula? So the s nth is equals to u plus a by 2 into 2n minus 1. U plus a by 2 into 2n minus 1. Yes or no? Clear? Chal. So then, so we have also seen two more standard results. So those are, if a body is moving from starting from rest, let's suppose, so a body is starting from rest. A body is starting from rest and it accelerates at a rate of alpha for some distance, and then it starts decelerates at the rate beta. So for some time t1 it accelerates, for some time t2 it decelerates. So finally it comes to rest. Okay. So in this case, so the relation between the times and the accelerations is given by t1 by t2 is equals to beta by alpha. So now, so for the same thing, for the same case, so where if the body starts from rest and then covers some distance at a rate of, so covers some distance at a rate of alpha and then decelerates, so at a rate minus beta, and finally comes to rest. So now, so let's suppose, so that this time is t1 and the total time elapsed, let it be t. So this time is going to be obviously t minus t1. We have seen the derivation in the last class, right? So now, so I can say that what is the maximum velocity? So here its velocity will become maximum. Here its velocity will become maximum. So what is that maximum velocity? Vmax. So which is alpha beta t by alpha plus beta. Alpha beta t by alpha plus beta, right? And then for the same situation, if you draw the velocity versus time curve for that, for this, if you draw the velocity versus time curve, so this is velocity versus time. So then see, first body it's increasing its velocity and here velocity becomes maximum. So it's starting from 0, its velocity increases, here it becomes maximum. So from there it starts retarding, so its velocity decreases, and finally it becomes 0 at this point. Now, so this is a Vmax, this is a Vmax point, right? So now what is the total distance covered by the body? What is the total distance covered? The total distance covered will be equals to the area under Vt curve, shall I simply say? So which is a area under Vt curve, area under Vt curve. So now I can write this as half into, so area of the triangle base. So from here to here the time t, and then so here time t into, so what is the maximum velocity? Height is nothing but Vmax. So then I can substitute it here, half into t into, this is alpha beta t by alpha plus beta, so that this is going to be alpha beta by alpha plus beta, 2 times alpha plus beta into t square. So this is a total distance covered. Remembered? So these are all standard results. If you remember, you can solve the questions easily in the examination. So that's why I'm just writing the standard results at a place. Okay, so clear this part. And then so we have also seen the graphs, right? So in the graphs, so what's the trick that I told you? So whenever if the slope tangents are like this, so they indicate the slope positive, right? So if the lines are like this, so they indicate the slope negative. So this is negative slope. and if they are flat like straight, so the slope will be 0 obviously. And then so we know that, so the ST curve, slope of ST curve results in velocity, so where if the slope is more, the velocity will be more. Velocity will be directly proportional to the slope. Right? This is about the ST curve, and we analyzed the different graphs, you already know that, right? So then, so next the VT curve, so the V versus T, so then the slope of VT curve will result in acceleration. The slope of VT curve will result in the acceleration. So here also the same thing. So the acceleration is directly proportional to slope of VT curve. And then, so we also know that the area under VT curve will result in the distance or displacement. So this results in distance or displacement. So if the given shape is above the x-axis, take it as positive area, and below take it as negative. Okay. Chal. So next thing, so the acceleration time graph. So related to acceleration time graph, so the only thing that you have to remember is, so the area under AT curve, so which results in the velocity or change in velocity we write. Okay, clear this part everyone? And related to the graphs, so we also discussed that, so if the graph is concave upward, so like this, if the ST graph, if it is concave upward, so then it's uniformly accelerating. Then we can say it's uniformly accelerating. So if ST curve is concave downward, so then it's uniformly retarding. So the concave downward case, it is going to be uniformly retarding. It's going to be uniformly retarding. Okay, and then, so what is the respective VT curve for this? So it's going to be like this. So this is a VT curve respective. And what is the respective VT curve for this? So the respective VT curve for this is, so like this. Understanding? Clear? Chal. So this is the part related to graphs. So and at the end, so that is Galileo's law of odd numbers. Just now we have seen. So that is the Galileo law of odd numbers. So what's the Galileo's law of odd numbers is? So if a body covers, a freely falling body covers, so some distances in regular intervals of time. So then let's suppose in the time t it covers distance s1. Okay, and then so in the next time period t, so let's consider it covers a distance s2. So then in the next time interval, so t, let's consider it covers the distance s3. So these time interval should be same. So then the relation between those distances will be equals to, so 1:3:5 and goes on. 1:3:5:7:9, so like that it goes on. Clear everyone? Understood this part? So hope I wrote everything here. So if any result is missing, just write it here guys. So I hope I wrote everything, every result. So just check once. Yes, so this I wrote, this one I wrote. Yes, so the distance covered in the nth second we wrote, right? Yeah. Yes, so and graphs also I wrote. Yes. So that's it guys from my end. So with this, the total motion in a straight line completed. So what you have to do is, so just how I wrote the summary, again write it on your own. Don't just follow this one. So follow it, but again write it on your own so that you can remember the things easily. Okay. So we'll meet in the next session, that is tomorrow, with the new chapter, that is motion in a plane. So where we are going to start the basics of vectors first. So then we'll go for the relative velocity and projectile motion. So till then, keep studying. All the very best guys. Bye. Take care.